Hello everyone, I'm Soumya Bhattacharya and today we are going to talk about the MVVM architectural pattern which stands for Model, View and View Model. By the end of this session, you won't just understand what these letters stand for, but why are we using this architectural pattern and why is this helpful? We often jump straight into writing code without thinking about the structure. But as your application grows from simple scripts to enterprise level systems, architecture becomes the difference between a project that scales and the one that collapses under its own weight. We aren't just going to look at how to implement the MVVM architectural pattern. We are also going to look at why it exists computationally. We will explore how separating your user interface logic from your business data leads to a system that is testable, maintainable, and robust. Before we start with the technical details, we first need to understand the reason for organizing a code base in the first place. Why can't we just write everything in the same file? Then we will introduce the core concept of the MVVM pattern. To make this stick, I'm going to use a clear restaurant analogy to explain how it works. And finally, we will examine the specific roles of the three main components, the model, the view, and the view model. Now look at the representation of the disorganized code that I have given here. We call this the spaghetti code. When you mix your data manipulation directly with the UI rendering code, you create what is known as tight coupling. If your database logic is hard-coded in your screen's activity or controller, fixing a bug in the database query might accidentally break the way the button is displayed. This makes the system fragile. A disorganized system becomes a maintenance nightmare because there is no source of truth. Every part of the code knows too much about every other part. We need a system where each class has a single responsibility, a concept known as the single responsibility principle. We need organization where everything has a specific deterministic role, ensuring that a change in the UI layer doesn't ripple down and corrupt your data layer. To make this abstract concept concrete, let's use a restaurant analogy. This is widely used because it perfectly maps to the responsibilities in software architecture. Think of the view as the customer. The customer doesn't know how to cook and they don't know the inventory levels in the fridge. They just want to consume the final product. They interact with the menu and place orders. The model in the kitchen is where the raw materials, here in this case is the data, are stored and processed. The kitchen is busy and complex. It enforces rules like don't serve raw food, which is the business logic, or we are out of a specific ingredient, which is the data validation. Now, the customer cannot walk into the kitchen and grab their own food, right? That would be a chaos. This is where the view model or the waiter comes in. The waiter is the essential intermediary here. They take the request from the customer, abstract it, and hand it to the kitchen. When the food is ready, the kitchen does not go out to the table. They hand it to the waiter who brings it to the customer. This separation ensures that the kitchen can focus entirely on cooking without worrying about the table etiquette. Now let's look at the model or the kitchen. In a computing context, model is the brain of the application. It is responsible for the single source of truth. This layer holds the raw data, whether it's coming from a local database, a REST API, or a cache. But it's not data warehouse. It enforces business logic as well. For example, if you're building a banking app, the model is responsible for checking if a user has sufficient funds before a transfer. It validates data integrity. If the view sends a negative number for an age, the model rejects it. Crucially, the model is completely unaware of the view. The code inside our model classes should not contain a single reference to a UI component. No Android views, no iOS UI kit, no HTML elements. This independence allows you to take the same model logic and reuse it across a web app, a mobile app, or a command line interface without changing a single line of code. Next, we talk about the view, which is the customer. This is the visual layer, the XML layouts, the Swift UI views, or the HTML DOM. The view has one job: display visuals and capture user input like clicks or text entry. We often say the view should be dumb. This is a technical requirement. The view runs on the main UI thread. If you perform heavy math, complex data storing, or network requests here, you will freeze the interface and lead to application not responding errors. The view should purely reflect the state given to it. It should not decide if a user is logged in. It should just show the login button if the view model tells it to. The focus is only on looking good and rendering the pixels. Now let's talk about the view model or the waiter. This component acts as the connector. Its primary job is state management. When the view receives an input like a button press, it delegates the action to the view model. The view model then requests data from the model. But here is the critical part. The model often runs data in a raw format, perhaps a Unix timestamp or a database cursor. The view cannot display that cleanly. The view model formats this data. It converts that timestamp into a string line like 10 a.m. So the view can just display it without thinking. Furthermore, the view model facilitates communication using data binding. This means the view model exposes streams of data, which are the observables. The view subscribes to these streams. When the data changes, the view updates automatically. This ensures that the view and the model never communicate directly, maintaining that loose coupling we discussed earlier. Now let's trace the execution path of a single user action to understand the communication protocol. It starts with the view. The user clicks a button, the view captures the interaction. The view calls a function in the view model. The view model determines what needs to happen, maybe fetching a user profile. It requests this from the model. The model performs the heavy lifting here, querying the database or hitting an API endpoint, and returns a result to the view model. Now, typically, the view model does not contain a function on the view like view.showData. Instead, it updates a variable inside itself, an observable. Because of data binding, the view is listening to that variable and detects the change automatically. This is called unidirectional data flow. Data flows from the model to view, and events flow down from view to view model to model. You still might be thinking that why do we engineer all this complexity? Why can we not write everything in the same file? To answer this, we'll talk about first the advantages and the benefits of the MVVM architectural pattern. First is testing. In a tightly coupled system, you cannot test the logic without an emulator or a browser because the logic is stuck inside the UI code. With the MVVM, since the view model and the model have no reference to the UI, you can write unit tests and run purely in your memory. You can simulate the model, feed data to the view model, and assert that the output is correct. This saves valuable time finding the bugs. Second is focused development. This architecture allows parallel work. A UI designer can work on the XML and CSS, which is the view, while a backend engineer works on the API and the logic, which is the model and the view model. They are not blocking each other. Third is maintainability. Changing the view, like moving a button or changing a color, does not risk breaking the core business logic because the logic doesn't live in the view. This leads to significantly fewer bugs over the product's lifetime. Now let's ground this theory in a concrete real-world example, which is a music player app. First, look at the model layer. In our music app, this layer is responsible for interacting with the file system or the streaming API. It stores the raw song file and the basic immutable facts such as the song name and the total duration in milliseconds or seconds. Note that the model doesn't care if the time is displayed as a digital clock or a radial dial. It simply ensures that the data, say 250 seconds, is accurate and available. Next, we move on to view model. This is where the data meets user requirements. The view model fetches that 250 seconds from the model, but a user cannot intuitively parse 250 seconds while listening to music. So the view model applies formatting logic to convert that raw integer into a readable string format like 4 minutes and 10 seconds. It also actively manages the application state, tracking Boolean flags like is playing or is shuffle enabled. Finally, the view displays a formatted 4 minutes and 10 seconds and captures the user's tap on the play button. Now, adding a few more technical details, how does this matter for the product development lifecycle? This separation transforms how a team builds software. During the development phase, we achieve focused development because the view and the view model are separate. A UI designer can completely redesign the play button or change the color scheme in the view file without even seeing the backend logic. Simultaneously, a backend engineer can optimize the database query in the model. They work in parallel, merging their code without conflict. Now, during the testing phase, which is the most expensive part of the life cycle, without MVVM, you need slow, flaky UI tests to verify logic. But here, because a view model is just a class with no UI dependencies, we can write fast unit tests. We can script a test that says if model gives 250 seconds, insert the view model outputs 4 minutes and 10 seconds. We can catch bugs instantaneously without launching an emulator. Also, during the maintenance phase, 6 months down the line, when you need to update features, the separation prevents regression bugs. You can refactor the heavy math in the model, and as long as the output remains the same, the view will never break. This drastically reduces the technical debt. Now, as we prepare to move into the practical coding session, I want to summarize what we have discussed so far. We started by identifying the problem that mixing data and design can create tangled, fragile code base that is a nightmare to maintain. We solved this by adopting the model view and view model pattern, which relies on strict separation of concerns. We designated the model as the independent brain that handles the business logic and data validation. We designated the view as the thumb layer strictly for showing visuals and user interactions. And we placed the view model in the center as an essential messenger, protecting the model and the view and managing state through data binding. Now let's discuss practical example together in Android Studio.
In this project, I have created a simple application that fetches user data from a REST API and displays it in the user interface. Now, let me walk you through the complete project structure and explain each component one by one. If you look at the lib folder, you will see that I have organized the code into different folders based on their responsibilities. We have a models folder that contains the data models. We have a service folder that contains the API service. We have a view models folder that contains the business logic. We have a views folder that contains the user interface schemes. This kind of folder structure makes the code very clean and easy to maintain. As the project size grows, you can easily find and modify the code as you need. Let's start with the model layer. The user model class represents the data structure of a user. It has properties like ID, name, email, phone, website, company, street, and city. All these properties are marked as final because we don't want them to change after the object has been created. The constructor uses required name parameters to ensure that all values must be provided when creating a user model object. I have also added a getter called full address that combines the street and city into a single string. The from JSON factory constructor is very important here. It takes a JSON map and converts it into a user model object. This is how we parse the API response. Additionally, also notice how I'm using the null aware operator with question mark and double question mark to handle null values safely here. Moving on to the service layer. The API service class is responsible for making the HTTP requests to the server. I am using the HTTP package here. The base URL is stored as a static constant. I'm using the JSON placeholder API, which is a fake free REST API for testing and prototyping. The fetch users method is an asynchronous function that returns a future of list of user models. It makes a GET request to the user's endpoint. If the response status is 200, which means success, it decodes the JSON response and maps each item to a user model using the from JSON factory constructor. If the request fails, it throws an exception. Now let us move on to the view model layer. The user view model class extends change notifier. Change notifier is a class in Flutter that provides the change notification to its listener. Here, it is the foundation of state management in our application. I have three private variables. Users, which is a list of user model, is loading, which is a boolean to track loading state, and error message, which stores any error that might occur. For each private variable, I have created a public getter. This is encapsulation. In the fetch users method, I have set is loading to true and clear any previous error message. Then I am calling the notify listeners to update the UI. Inside the try block, I have called the API service to fetch users and store the result. If any error occurs, it catches and stores the error message. Finally, is loading is set to false and called notify listeners again. This pattern of setting loading state, making the API call, handling errors, and notifying listeners is very common in real world applications as well. The user list view is a stateful widget. Inside the init state, I am using widgets binding.instance.add post frame callback to call fetch users after the first frame is rendered. This ensures that the context is available and the widget tree is built. I am also using provider package for dependency injection and state management. The context.read method is used to access the view model and calls the fetch users method. In the build method, I am using consumer widget to listen to changes in the view model. The consumer widget builds only when the view model notifies its listeners. Inside the builder, we first check if the data is loading. If yes, I show a circular progress indicator in the center of the screen. Next, I check if there is an error message. If yes, I show the error message along with the retry button. When the user taps the entry button, it calls fetch users again. If there is no loading and no error, I show a list view.builder that displays all the users. Each user is displayed in a card with a list style. The leading shows a circular avatar with a random image from picsum.photos. The title shows the username, the subtitle shows the masked email using a string extensions. The trailing shows the user ID formatted using integer extension. When the user taps on a list item, it navigates to the user detail view screen. The user detail view is a stateless widget that takes a user model as a required parameter. The app bar tile shows the user initials using a string extension. The body has two main sections, a header and an information section. The header shows a large profile picture, the username, the formatted user ID, and a chip showing the original position like first user, second user, and so on. The info section displays multiple info cards. Each info card shows a title, icon, and a value. We display the email, phone, company, address, and website. The info card is a private widget. Here, the info card is a private widget class here that creates a consistent card design for each piece of information. Lastly, we go to the main.dart file. The main.dart file is the entry point of the application. I am wrapping the material app with change notifier provider. This provides the user view model to all the widgets in the widget tree. The create parameter takes a function that creates a new instance of user view model. Any widgets Below this, provider can access the view model using provider.auth, context.read, or context.watch. So this is how you can implement the MVVM architecture pattern in Flutter. It has several benefits which include separation of concerns, testability, maintainability, and reusability.
So to wrap up, here is your MVVM cheat sheet. If you remember nothing, just remember this. So in MVVM, the model handles data and business logic independently. The view manages display user interactions only. And the view model acts as an essential connector and a messenger. MVVM prevents direct communication between the model and the view. Organizing code this way simplifies future maintenance and makes you a better developer. Thank you so much for your time, and please feel free to ask any questions.